Today's discussion would be on rotational conformers. As you know, molecules at room temperature would be not stagnant, but just rotate and do several kind of motions. One of the motions that is common in hydrocarbons, for example, is a free rotation across the sigma bond, that is the carbon-carbon bond. So they are always free to rotate and they can adopt different conformational states. So, for example, if you were to take ethane, which is a hydrocarbon with two carbons, you would have, for example, just at least if we are just showing two conformers, these are called conformers. That means different rotational states of a molecule. So if you just take this molecule, which is ethane, starting from this conformer or from this rotational conformer, where you have this hydrogen and that hydrogen are 60 degrees apart. That means if you have something like this is a blue hydrogen right there, and this hydrogen right here is at 60 degrees. Obviously, this hydrogen and that hydrogen are at 180 degrees. Such conformers are called staggered, meaning that they are not facing one another. For example, in this conformer, if you just look at here, this hydrogen and that hydrogen are facing each other. If you just see the model here, where you have the two conformers, where you have all of the hydrogens, this hydrogen and that hydrogen, this hydrogen and that hydrogen, and this hydrogen and that hydrogen are totally facing each other. That is called an eclipsed conformer. So we have staggered, where you have at least this hydrogen and the next hydrogen are not facing each other, rather they are at 60 degrees. And additionally, if you just look at this hydrogen and that hydrogen, they are at 180 degrees. Such conformer is called staggered. As you know, the rotation is very random and they could adopt different conformation. What we are just showing here is as a model or as an example when they adopt different states of conformation. For example, if you just rotate by 60 degrees, if you just rotate this that way, this hydrogen becomes up. So if you just fix this and just rotate this one by 60 degrees, you would face this kind of conformer. But the molecule obviously doesn't stay like that, it continuously rotates. So the angle between these two, the angle that we always see, is called a dihedral angle. A dihedral angle of 0 means everything is eclipsed. So this is 0 degrees between these two. Between these two is 0 degrees. Between these two is 0 degrees. So this conformer, this particular conformer representing this one, is called an eclipsed conformer. So the dihedral angle, which is the angle between each one of these bonds, is 0 degrees. But if you just look at this one, each one, for example, this hydrogen and that hydrogen are at 180 degrees. This hydrogen and this hydrogen are at 60 degrees. This hydrogen and that hydrogen are at 60 degrees. So they are staggered, and usually we take on the two carbons the extreme hydrogens, which are on opposite side. So this is actually 180 degrees. So they are called staggered. So the way they look on a model is this. If you just look at this model, you have this hydrogen and that hydrogen are at 60 degrees. But importantly, this hydrogen and that hydrogen are at 180 degrees. So this is one other conformer. So a molecule especially hydrocarbons, with sigma bonds. Remember, it's sigma bonds that could rotate. They are free to rotate at room temperature, or at any even low temperature, they are constantly rotating. So there are two concepts now I want you to remember here. A dihedral angle is the angle between the bond, here for example, this bond and this bond are just facing each other, and the dihedral angle is 0 degrees, and they are called eclipsed. And here the staggered one is where you have this bond, for example, and that bond are at 180 degrees. So that is the dihedral angle. For these two conformers, if you were to evaluate their energies, the energy of the staggered is low energy, and the eclipsed is high energy. So remember now, the eclipsed, because of the interaction of the bonds between these two, and as well as steric hindrance. Steric means the bulk of whatever you have here. For now, we have just hydrogens, which are small. Still, there would be any additional steric factors. So, in any conformational, rotational conformer, if you are just were to evaluate energies, you evaluate one, the torsional strain, torsional, and also the steric energy. Sterics. Steric means the mass, the bulk, how heavy or the interaction is facing each other. So the volume of this substituent and that substituent, if they are coming into close contact, there is a steric clash. The torsional is the bonds, the interaction between these two. That is another strain. So the energy is contributed by both torsional strain and steric factor. So remember, these two factors are contributing for being low and high. So in terms of the sterics, the hydrogens are not facing each other, so there is still not high steric factor in the staggered form. Here there is a steric clash as well as the torsional strain. The torsional strain is the interaction between the two bonds that are facing each other. So if you just look at this eclipsed, this is staggered one, there is no torsional strain, or at least this bond and this bond are 60 degrees away to each other. But when you have all eclipsed form like this bond is interacting with this bond. That's not favorable because these are electron density. As you know, they are sharing 2 electrons. There are 2 electrons here. So it is always repulsive because they are of the same charge. And the other thing is, if you have a large substituent here and that substituent, they could come closer and cause steric hindrance. Therefore, in conformational analysis, or when you evaluate energies of 2 conformers, you should see whether sterically it is stable, and also if there is a torsional strain. Torsional strain is when the bond is exactly facing the other bond, there would be a repulsion. So in the next discussion, we'll see with energy profile or energy diagram by just rotating each one of this at different times. And we can also look at compounds that are with more carbon than just 2 carbons. These are ethane, which are the simplest form to display conformational analysis. But in the next discussion, we'll bring propane and see different conformational conformational states. Now, the difference between these 2 conformers, between the low and high, is about 12 kilocalories per mole. What it means is this one is 12 kilocalories per mole at higher energy than this one. So how does the 12 kilocalorie came? Each one of the steric factors between two hydrogens is about 1 kilocalories per mole. So how many we have? 1, 2, 3. Those are 3 kilocalories per mole. Then each one of the strains, the torsional strain, you have this, and interacting with this. So this bond is interacting with that bond, facing exactly at 0 degrees, and that is interacting with that. So each one of them would be contributing about 3. So there are 4 of them. 4 times 3 would be 12. So 3 times 3 is 9, plus the 3 steric factors would contribute 3 and 9. That would be about 12 kilocalorie per mole. We'll see that in detail in the next discussion. Continuing our discussion on conformational analysis or conformers, one of the most recognized pictorial designation of conformers is called Newman projection. So the Newman projection has this kind of models to show different conformers. You have a circle where you are just looking at this carbon, for example. If this is the carbon at the center, this carbon right here, there are 3 hydrogens that are attached to this carbon. So this carbon is, as you look to the front like this, if you just look at this is a carbon right there. So behind is the other carbon. So the Newman projection just shows you front there are 3 hydrogens, and the fourth bond is where you have the second carbon. So this is what you are just looking at right now. You have the front 3, which are in the circle, and there are 3 of them at the back. So just it's looking through this carbon. From your side, if you are just pointing to this carbon, that's what you see. So in this carbon, the red ones are at the back, and the blue ones at the front while just looking at this. So this is from our previous discussion, this is eclipsed. The eclipsed form, which is also at higher energy. So the Newman projection always shows 3 hydrogens or 3 substituents from the front, and the back there are 3 substituents or 3 hydrogens. So remember how and become very familiar how to draw Newman projection. So make sure that what you are looking at the front is 3 substituents. 3, it could be carbon, it could be hydrogens, but exactly what you see in the front are 3 substituents or 3 items. At the back, similarly on the next carbon. So Newman projection is a projection between 2 carbons. You should always choose 2 carbons. Now we are choosing these 2 carbons for our Newman projections. Always a Newman projection is a projection through 2 carbons. So you always pick which carbons you are looking at. So between this projection is always between 2 carbons. Even if you have a very long chain of hydrocarbons, you should always say, okay, I am projecting or I am drawing my Newman projection through carbon 4, carbon 5, example, carbon 2, carbon 3. It could be carbon 1, carbon 2. So it's always there are 2 carbons on which there are different substituents, and the 3 are the front and the 3 on the other carbon are at the back. Here is the simplest form where you have 18, all of them are hydrogens. So this is the eclipsed form. If you slightly rotate or by 60 degrees the back one holding the front, That means if you just rotate the back by 60 degrees, you would end up this projection. So the Newman projection in the blue shows you the front ones, and at the back you will see the red ones, which are 60 degrees apart. So the dihedral angle here is 60 degrees. The dihedral angle between these two is 0 degrees. So you should be familiar whatever degree of rotation you have. So if you just were to rotate this by another 60 degrees, you end up another conformer. That conformer, for example, if I rotate another 60 degrees, I will have another eclipsed form of the same thing. So another 60 degrees, keeping the blue ones at the front, hydrogen, hydrogen, hydrogen. These red ones now become overlapping at this position here. At this position. So after you have eclipse form, 60-degree rotation, you get staggered form. Staggered. Now if you rotate it again by keeping the front fixed and just rotate the red ones, you would end up at another eclipsed form. So the rotation continues 360 degrees. Now we rotate it by 60 degrees, another 60 degrees, 120 degrees. We can rotate another 60 degrees. So most of them, for example, energy-wise, this is the same as this one. So energy-wise, they are the same. When you just look at this, the same hydrogens are eclipsed, the same torsional, and the same steric factors. So I encourage you to draw Newman projections with 3 items to the front and 3 items at the back, and always choose which carbons you are projecting it from. So in the next discussion, we will draw a Newman projection and evaluate each conformer, and we will see what the conformational states or what the energies are for propane. Propane has 3 carbons, therefore we can choose carbon number 1 and carbon number 2 as our projection carbons. Now let's pass on to hydrocarbon, propane, which has 3 carbons, and let's practice on how to draw the Newman projection. So in drawing a Newman projection, first you have to choose which carbon you are projecting it through. For example, in propane you have 3 carbons. Now I'm choosing carbon number 1 and carbon 2. It doesn't matter, it could be from this carbon 1 or carbon 2 as my carbons that are fixed for the rotation. So now if I'm just taking that carbon, this is that carbon right there at the center, is carbon 1. So carbon 2 is containing what? Carbon 2 is containing 2 hydrogens and 1 metal group. So as you say, always in the Newman projection, you should have 3 at the front, 3 at the back. So at the back, you would have 2 hydrogens, which are on carbon number 2. Still on carbon number 2, there is CH3, which is this. So when everything is eclipsed, it looks like this. So looking at this carbon right there, for example, if you have just looking at this carbon, this is actually staggered. Actually, this is eclipsed. So if you have something like this, you have all hydrogens aligned, all the hydrogen and CH3 are eclipsed here, and 2 hydrogens. So this is just looking at straight through this carbon here. So there is CH3 and also 2 hydrogens that are eclipsed. 2 hydrogens, this hydrogen and that hydrogen are eclipsed, and this hydrogen and this hydrogen are eclipsed. There are 2, and this CH3 and that hydrogen, which is this one, are eclipsed. So that's how you would be just visualizing it, by just looking at like this. You are just looking through that carbon, meaning this carbon right there. You would have the two hydrogens eclipsed here, and one CH3 and H eclipsed. But if you just rotate by 60 degrees, the same on the same conformer, all the red ones fixing the blue ones, the hydrogen would be now 60 degrees away, and this hydrogen would be 60 degrees away, and this hydrogen would be 60 degrees. That also is moved to in between this, which is the CH3. So this is a Newman projection for propane. And the energy difference between, always, as I already told you, the energy is contributed by torsional and also steric factors. So the difference between the eclipsed and the staggered one is about 14 kilojoules per mole, where the eclipsed become high by 14 kilojoules per mole, and the staggered is low energy. So if you just rotate, you'll end up also in the same conformer like this one. So the next one, if you just rotate 60 degrees, you'll end up similar to this kind of conformer. Excuse me. So this is 14 kilojoules per mole. I think in my previous discussion I have mentioned as 12 kilocalories per mole for ethane, but the units are off. Remember to correct it to be kilojoules per mole. It's 12 kilojoules per mole for ethane, and 14 kilojoules, not kilocalories, per mole for propane. So what are the contributions? Remember, we have said each hydrogen-hydrogen interaction is contributing 4 kilojoules per mole. That means 3 from torsional strain and 1 from steric factor. So if you just were to calculate this one, okay, this one contributes 4 kilojoules per mole. This pair contributes 4 kilojoules per mole. That's 8. So 2 times the hydrogen-hydrogen is 8 kilojoules per mole. But remember now, this is a new one where we haven't seen this before. This is a metal hydrogen. A metal hydrogen eclipsed form contributes 6 kilojoules per mole. That means you have a steric plus a torsional contribution that adds up to be 14 kilojoules per mole. So remember, each hydrogen-hydrogen steric plus torsion contributes 4 kilojoules per mole. Now we are introducing a new interaction between a metal and a hydrogen, because metal is now larger than hydrogen, so the contribution is not 4 but rather 6 kilojoules per mole. So the difference between the eclipsed form and the staggered form is 14 kilojoules per mole. So we'll be practicing now. In the next discussion we'll see now butane, which has a 4 carbon, and it is very interesting to see the different interactions that we haven't seen would come up in the discussion of butane conformers. So now, as a review, practice how to draw a Newman projection. Select 2 carbons. Those 2 carbons should have 3 substituents in each one of them, 1 behind, 1 from the front. So always in the drawing of Newman projection, you should have picked always 2 carbons through which you would project to see the other substituents. So in the next discussion we'll evaluate butane. Now let's look at butane conformers with energy diagram with various dihedral angle variation. So if you just take butane, you can take any 2 carbons to draw the Newman projection. For this case I have just chosen carbon number 2 or carbon number 3. here are the 2 carbons I chose as my point of reference for the Newman projection. So when you take these 2 carbons, for example, in this carbon, you will have 2 hydrogens and 1 metal group. On this carbon, you would have 2 hydrogens and 1 metal group. So regardless, you can start from any conformer you want, but you should be consistent during the rotation. So let's just start by rotating it, starting from the totally eclipsed to a totally staggered conformation. So let's go step by step. So at 0 degrees, that means all dihedral angles are at eclipsed form, that is angle 0. The energy of that molecule is 19 kilojoules per mole. Remember, we have 12 kilojoules per mole for ethane conformers and 14 kilojoules per mole for propane. Now, butane has 16 kilojoules, 19 kilojoules per mole. So let's see each one of them. So if you just look at here, you have 1 CH3 staggered. They are sterically bulky than hydrogen. Now the energy would be increased because of all this interaction. There is a torsional strain because they are at 0 degrees. Again, you have added 1 CH3 interaction. So remember, this is 19. So each hydrogen eclipsed form, we have said that they contribute 4 kilojoules per mole. That means 4 plus 4, 18. So 1 CH3 eclipse interaction, CH3, it means that it is 11 kilojoules per mole. Because 2 hydrogen eclipsed interaction is 8 kilojoules per mole. So remember this. So we are now plotting energy versus the angle of rotation for each conformer. So let's start from the eclipsed form, which is 19 kilojoules per mole, which is an eclipsed form where you have a very high steric interaction between 2 larger groups than hydrogen, CH3, which has 11 kilojoules per mole. So the next 60-degree rotation would give you this conformer, right? The next is, it says 3.8 kilojoules per mole. It's a very low, very stable kind of interaction. So one gauge in this conformer is called gauge interaction. Between these 2 sterically bulky groups, this interaction at 60 degrees is called gauge interaction. So one gauge interaction between metal would give you about 3.8 kilojoules per mole. That's why the energy is raised. Otherwise, it is totally staggered. But here, the interaction is gauge because they are 60 degrees only apart. So the steric hindrance still exists. They are very close enough to cause the gauge interaction. So gauge interaction, now it's a new concept. A gauge interaction is between 2 large groups at 60 degrees is called a gauge interaction, and it's relatively higher energy. So that is 3.8 for CH3 gauge interaction. Now the next one, if you just rotate this by 120 degrees, by 60 degrees rather, the energy is 16 kilojoules per mole. Let's evaluate this. So if we just evaluate this 16 kilojoules per mole for this at 120 degrees, what do we have? We have obviously 2 hydrogens that are eclipsed, and we know the value 2 eclipsed hydrogens. 2 eclipsed hydrogens produce 4 kilojoules per mole. So 4 kilojoules per mole, and now you are left with 12 kilojoules per mole. So each eclipsed CH3H, remember we have also discussed it in a ethane conformer, each eclipsed CH3H would produce about, this is 4, therefore each one produces 6 kilojoules kilojoule per mole for CH3H in eclipsed form. CH3H, that is 6 kilojoules per mole. So 6 plus 6 is 12, 12 plus 4 is 16. So that's why you see it's not as eclipsed as this one at 0 degrees. This is 19, but this is at 16 kilojoules per mole higher in energy. So as you go, this is the highest energy at 19 kilojoules per mole at 0 degrees. We rotated it by 60 degrees, we end up at 3.8, which is a relatively low energy. As you see, this is 3.8 at 60 degrees. Now the next one is raised. The energy is raised because all are eclipsed in eclipsed conformers, and each one of them produce, this is 4 kilojoules per mole. Each hydrogen eclipse contributes 4. So now let's rotate this by another 60 degrees. So you end up having this hydrogen to be here, having this metal group right there down, and rather this hydrogen would be here. As you see this conformation, remember, is 180 degrees between the two large group. That's called anti. Gauche is when the two large groups are 60 degrees away. But when the two interacting groups, the two larger group in your conformer, are at 180 degrees, that is the lowest energy here. This is the anti position. Anti-conformer produces the lowest conformer energy. So this is the lowest according to energy, and the total eclipse is the highest. Obviously, there are intermediate energies, so you can follow all of the on the graph, and the next ones are, if you just rotate by 60 degrees, you can find one of this again. So we rotated it up to 180 degrees, so you can practice by rotating it by 240 by 60 degrees. That ends up to be 240 degrees. That is equivalent to the 120 degrees. It will be like this conformer. So this, the last one at 360 degrees, would look like similar to this. So this is the energy diagram versus different conformers at each dihedral angle. So if you draw the energy versus, this is energy axis, and those are dihedral angle theta in degrees. So you'll evaluate each one of the conformers, and you'll evaluate what the energy looks like. So I encourage you to practice with different conformers of higher hydrocarbons like pentane, hexane, and so on. But no matter what, you only have to choose only 2 carbons for your conformers. For example, if I had chosen this, if I had chosen this and this, those are different kind of conformers. The front carbon, for example, would have 3 hydrogens on it, but this carbon would have 2 hydrogens, 1 ethyl group. So that's a different kind of conformer. So you can choose any of the carbons and see what the conformers look like and evaluate which one has the highest and which one has the lowest energy. So for the butane, for these conformers, we chose carbon number 2 and carbon number 3. So with this, we conclude the discussion on conformations of alkanes and their respected energies.